take a look at the first question of this passage. The ligand of HMPR alpha is derived from which compound? All right, let's take a look back at the passage to see what the ligand is. We know that the steroid progesterone, and researchers interested in studying the membrane progestin receptors. All right, so these are receptors for progesterone. Okay, that is the ligand. The progesterone is the ligand. We know this because HMPR alpha is a type of MPR, and MPR is a membrane progestin receptor. So again, we know that this MPR is going to be binding progesterone, making progesterone the ligand. So what is this progesterone? This is where the discrete knowledge has to come in here. First, you need to know that progesterone is a hormone, okay? And most importantly, specifically, it's a steroid hormone, okay? Now, this is where your second bit of discrete information has to come in, knowledge has to come in. You have to know that all steroids, they're all derivative of cholesterol, okay? So if you look at the structure of cholesterol and look at the structure of all of these steroid hormones, you're going to notice that they're actually very similar. And so this is just after that, after noticing what the ligand is for this HMPR alpha, this is just all discrete information that points you to the fact that the ligand is derived from cholesterol. Not glycerol, not this amino acid, and not this sugar especially. Let's take a look at the next question here, which says the second purification step is which type of chromatographic separation? So what is the second purification step? The second chromatography step, which utilized histidine 6-tag. All right, so the second chromatography step is going to be the one that requires this right here, okay? And we know that this sequence, this histidine binds onto the nickel cations. Now, this is another type of discrete. You do have to know the difference between affinity, size exclusion, cation exchange, and anion exchange. I'll go over all of these really briefly, but affinity is when you have some kind of molecule, so let's say you have a protein, and you run it through a chromatography tube, and essentially what happens is, let's say this protein likes to bind onto this little molecule here, then what that means is while every other protein that you don't want is going to be, it's going to be just flowing through, the proteins that you do want are going to be stuck onto these guys that they like to bind onto. And so that way you can get rid of everything you don't want, and then what you're just left with is this tube with a bunch of proteins that you do like, just bound onto like the side of the tube, because they like to bind onto these little molecules on the side. This is affinity chromatography. Now, size exclusion, this is different. As the name implies, this is going to be dependent on the size. And usually what happens is you're running a column with some kind of gel. I believe they use things like dextrose. I'm not exactly sure, but for the sake of the problem, I'm just going to say some type of gel or some kind of porous material like beads, these beads that have holes in them. And what's going to happen is, let's say we zoom in into this bead, and it says this bead is hollow, okay? Let's say it's hollow right here. All right, let's imagine this is going through this little hole is going through the bead. And if you have, these molecules that are too big, they're not going to enter these holes, okay? They're going to just flow right down the column, all right? But if you have these molecules that are smaller, so maybe the red molecules are a little smaller, they can actually fit into these holes. And what's going to happen is it's going to go into these holes of all of these beads. Let's say these are the beads. And let's say this molecule, this smaller molecule is going to get stuck into these beads, okay? Because it can get stuck in these holes. So as it flows down, it gets stuck into these inside of these holes. It's not going to flow as fast. And so what happens is the bigger molecules, okay, the bigger molecules flow faster, and the slower molecules, because they get caught up in these holes, because they're slowed down, they're going to go through a little slower through the size exclusion chromatographic tube. And it does discriminate based on size, so maybe like a medium-sized molecule, it's not going to go as fast as a blue-sized molecule, but because it's bigger than at least the red-sized molecule, it's going to go a little bit faster than the red guy. So it does differentiate on size. Just know that the bigger ones go faster. Now, cation and anion exchange, these are exactly the same. The only thing that's different is it's kind of similar to affinity chromatography. And here you have some charged molecules here. And let's say this is negatively charged, okay? Let's say these molecules are negatively charged. Let's say you have a lot of proteins, and the proteins you want, you know for a fact that they're going to be positively charged, okay? So what's going to happen is the positively charged proteins, they're going to get stuck, they're going to get attracted to these molecules, they're going to want to hang out a little bit more, they're going to flow through this column slower, okay? But for the ones that are, negatively charged, or maybe just neutral, okay, neutral, 0, they're not going to, especially the negatively charged molecule, they're not going to be really attracted to the side, side molecules here, the ligands on the side of the column here. So they're just going to pass right through really fast. And the more positive the molecule is, the more positive it is. You know, maybe it's just +1 versus 2 plus versus, you know, 3 plus. The more positive it is, the more strongly it's going to interact with these side molecules over here, which are negatively charged, stuck onto the, you know, the side of the tube, and the slower they're going to go through the column, okay? And the difference between cation exchange and anion exchange is when the side, you know, these molecules here are negatively charged, and anion exchange is when these guys on the side are positively charged and not negatively charged. So cation exchange is when the protein that you want is positively charged, and the anion exchange is when the protein that you want is negatively charged. So definitely review these. I'm just going over these kind of briefly, maybe not satisfactorily for you guys, but I do want to just briefly remind you guys what these different types of chromatographic techniques are in case you guys do need a refresher. So keeping this in mind, if we think about what nickel and histidine is, well, this, you know, it's a little bit tricky because nickel is going to be charged. They just tell us that nickel is going to be charged, but it's not the charge that's going to be bringing the protein with the histidine tail, you know, histidine 6 on it. The histidine isn't attracted to the nickel because of its charge, or yeah, the histidine itself is actually just naturally has a high affinity for nickel. It likes to bind onto nickel. So even though some people might choose cation exchange here, I mean, we know for a fact this is a size exclusion or anion exchange. Some people might choose cation exchange. It's not cation exchange because we're not relying on the fact that histidine is charged to bind onto nickel. It's the histidine itself, okay? Histidine itself just has a natural affinity for the nickel ion. Again, because histidine itself is not charged, we're not relying on histidine's charge. Rather, we're relying on histidine's natural affinity for nickel. That's what makes the answer A and not C in this case. All right, let's take a look at the next question here. It says the structure of compound 2 is shown. What structural features are most important for the functioning of this compound as described in the passage? All right, what is compound 2? What is compound used for? It says H-MPR alpha was then extracted from the membranes using N-decyl beta D-maltopyranoside compound 2. All right, so what is H-MPR alpha? Remember, it's a membrane receptor. Okay, so let me just draw this out real quick. You have your membrane. Okay, let's do this. Your membrane. All right, these are your. I'm drawing up the lipid bilayer here. All right, and then you have this receptor. Okay, let's say this is the receptor that you're interested in. Now, if we need to get rid of this, take this receptor out of the membrane, and we're using this molecule, well, how would we do that? We would actually just dissolve away the membrane. And how do we do that? We use detergents, okay, or soaps, or detergents would be the best. No, I forgot the other word for it, but yeah, detergents. And what are detergents? These are things that can actually dissolve away these guys. And how do you dissolve away these lipid membranes? Remember, these are both hydrophobic and hydrophilic. Each of these phospholipid membranes, or phospholipids, they have a hydrophilic head, okay, and they have a hydrophobic tail. And so how do you dissolve something that's both hydrophilic and hydrophobic? You use something that's also hydrophilic and hydrophobic. That's why when you want to dissolve membranes, you use detergents. Detergents also have a hydrophilic head and a hydrophobic tail. So if you insert something that's also hydrophobic and hydrophilic, okay, it's going to get rid of all of these different phospholipids, freeing up our little receptor here from the membrane as well. So what structural features are important in compound 2? So you'll notice this is also hydrophilic and hydrophobic. You have this huge hydrophobic tail, okay? If I can just send this to the back. There we go. Yeah, this huge hydrophobic tail, and then you also have a bunch of hydrophilic elements here. You have all of these hydroxyl groups, all of these alcohols that can form hydrogen bonds. So this is also hydrophobic and hydrophilic, and this is what makes this a great way to dissolve membranes and release that receptor protein that you're interested in. That is why C is the right answer here. Again, detergents are used to dissolve membranes. This is an example of a detergent in that it has a hydrophilic head and a hydrophobic tail that is great for dissolving membrane bilayers, which also are constituted of phospholipids that are both hydrophobic and hydrophilic. Now, if we look at the other answer choices here, let's go around and see what's wrong. Presence of a reducing sugar. A reducing sugar isn't going to be the reason why this is going to be good. A reducing sugar, it could be non-reducing, it could be reducing. It doesn't really matter. The sugar identity itself is not the critical factor in dissolving this membrane to release the protein. All right. Multiple hydrolyzable linkages. Again, hydrolysis is not what's going to be releasing this protein. There is no hydrolysis that happens when you're dissolving out the membrane. And specific configuration of numerous chirality centers, again, the chirality doesn't matter. It's not really specific in when you're dissolving the membrane, as far as I know. And so, again, the chirality, these chiralities could have been all different, and it wouldn't have mattered in dissolving this, this membrane here. The most important feature was the hydrophobic and hydrophilic regions. This is a little bit more basic gen chem here. How many moles of NaCl were contained in 500 milliliters of the buffer solution used to elute HMPR alpha? So what's the molarity of this? Let's see. 300 millimolar. Okay, the buffers contain 300 millimolar of NaCl. 300 millimolar, what does that mean? It's 300 times 10 to the negative 3 molar. Well, what is moles? Molar is equal to 300 times 10 to the negative 3 moles per liter. All right, 500 milliliters, that's 0.5 liters if we do the conversion. So if we just multiply this out, 300 times 10 to the negative 3 mole per liter times 0.5 liters, we can cross out the liters, we get 150 times 10 to the negative 3 moles. All right, so let's see. And that's exactly this answer choice right here, D. The other ones just don't make sense with this math. So make sure, again, do the math carefully, do it correctly, do it accurately. You don't want to miss out points on questions like this, where it should be relatively simple compared to some of the other questions. All right, let's move on to the last question of this passage, and it says, which experimental evidence suggests that the purified HMPR alpha obtained by the researchers was in its native state? The HMPR alpha that was obtained blank. All right, it says A, retained both the compound 1 and histidine 6 tags. This doesn't tell us anything about the state of the protein, so regardless of if the protein was folded up properly or if it's completely denatured, right? Denatured means unfolded. So even if it's unfolded, it can still, it can still hold on to its tags at the end, right? So it doesn't matter if it's folded up properly or if it's completely denatured, it's going to retain both of those tags. So this doesn't tell us anything about its native state. B says, was purified by 2 separate chromatography steps. The purification step doesn't depend on whether, the ones they did at least, doesn't depend on whether these were denatured or fully folded. As a matter of fact, during these purification steps, it's more likely that they were completely denatured. So again, the fact that it was just going through the 2 chromatography steps doesn't tell us about whether this protein was completely folded or unfolded. As like I said, it doesn't. Yeah, it was likely probably actually denatured completely. Let's look at D first, and it says had a nearly identical molecular weight to HMPR alpha obtained elsewhere. So if you look at this protein here and this protein here, as long as the sequence is the same, the weights are going to be exactly the same, right? The amino acids with the same weights. If the same amino acids constitute each of the proteins here, that means each of their molecular weights are going to be exactly the same as well, even regardless of whether or not they're completely folded into their native state or if they're completely denatured, like we see on the right. So even if they have identical molecular weights or nearly identical molecular weights, they're not going to tell us anything about whether or not this protein is folded. Finally, it says C exhibited a binding affinity for progesterone that was similar to that exhibited by native HMPR alpha. All right, guys, remember the binding of these proteins. So when a protein binds another substrate, that binding depends on the binding pocket, the shape of that binding pocket, right? So let's draw a protein. So if I want to bind something in this pocket, this protein has to be completely folded. If it's denatured or if it's misfolded, it's not going to bind that substrate as efficiently or at all. So if it's able to bind progesterone with the same binding efficiency as the native HMPR alpha, this tells us that, okay, this HMPR alpha that we obtained has to be the same shape, and that same shape means that it has to be in its native state as well. So again, if in order for it to bind progesterone with the same binding affinity, the only way that could have been done is if it was completely folded in the same way the native HMPR alpha was folded as well. Therefore, it must have been, the one we obtained must have been its native state as well, making C the correct answer.